We're happy to have Yoav Levine with us today. Yoav did his PhD at BYU with Chinchilla, working on very interesting both the theoretical aspects of deep learning and quantum physics, and later working on transformer models. We tried the backbone of NLP today. He won many awards, including the Levine PhD 2021 award here. In the last 2 years, he's been co-chief scientist at AI21, a startup from Yoav Shah, and Chinchilla, and Chinchilla, again, developing large pre-trained language models and working on research on how to use them and apply them. So very excited to hear you talk today.
Thank you, Jonathan. Kind intro. I'm very happy to talk to you guys here today. This doesn't come as a surprise to anyone in this room. Something's happening in natural language processing. But if we were to look at superficial signals for this, so people are submitting more papers to NLP conferences. There was some baseline, and circa 2018, something happened. From another point of view, the deep learning models being trained in the industry have grown by a factor of 1000x to almost 500 billion of learned parameters. Now the largest ones today, and it's not expected maybe to stop. If another superficial signal is the products, the text-related products that we all as users are using, Google Docs and anywhere, a lot of them, and they cross the usability threshold. The people start paying money for them. The number of the income or the number of dollars paid for NLP products was $3 billion in 2017. Has grown by 7 or 8x by today, and it's not projected to stop. This growth is with another 10x factor projected to be by 2030. So it's a bit of an understatement to say that something's happening. And what happened? Okay, what happened around 2018? We call it in our community the BERT moment, analogous to the ImageNet moment that the computer vision guys had a decade ago. And it's a moment where an algorithm or an architecture comes and sweeps the leaderboards, closing the gap to human performance from previous state-of-the-art. And it really was a moment because October 2018 was the archive, and by December, you had to go all the way down to 9th place in leading NLP leaderboards in order to find a non-BERT-based architecture. So what is the algorithmic foundation for this revolution? Firstly was the architecture, Jonathan mentioned. A paper came out mid-2017 about transformers. Attention is all you need, so I'm going to use the words transformers and self-attention interchangeably. Self-attention is the mechanism at the heart of these transformer networks. And what BERT did in the BERT moment, they married this strong architecture with the ability to learn from the internet, from unsupervised, unlabeled text. So they applied this architecture over the web, and we were able to train a network over that at a high level. Another important moment that happened around a year and a half after BERT came out, we call it the GPT-3 moment. Can't ignore it. It's where an architecture was trained at an unprecedented size for a neural network, 500 times the original size of BERT, which was already pretty big. And with this scale, with this size, we saw emergent phenomena that really had an impact on the field. These models, without training at all, without updating their learned parameters at all, were able to pick up demonstrations or instructions from humans set in natural language and perform tasks as they were described to them by humans. Okay, and this emerged with scale. And had a big impact on the industry. So we have to add to these pillars of the revolution, the architecture and the ability to train over raw text, and everything at unprecedented scale. 1 trillion parameters for a neural network is unprecedented. 2 trillion words that these models are trained on, so 2 trillion training examples, you can think about it like that. And with this big increase, there's also the price tag. Okay, so the compute has grown obviously with these models. The y-axis is exponential. And GPT-3 was already said to be around $10 million to train a single model, which is a heavy price tag. My talk is going to be about, with this atmosphere of graphs going up, the importance of principled guidelines. This revolution has mainly been led by a tremendous empirical pull in the field, which is great. This is how this cutting-edge NLP revolution has come to us. But there are, I'm going to argue, we're going to discuss some drawbacks for why we still need to stop and think about how we do this, even in this success. So firstly, the price tag and these models put us in a position where there's a uniquely high commitment to design choices. Yes.
Can you please explain what is the cost of the model?
Yeah, it's about having a very big neural network being applied to a lot of training examples. So the cost is in cloud compute where you hold you pay that to Amazon or Google.
And you do
They
it
get the
from
money.
every time you count it from scratch.
If you pre-train it from scratch, you randomize the network, and then you want to have a language model in the end, you apply it over the entire internet. That's what costs you.
And you was that on the previous slide was from
Yes.
scratch?
Yes.
Okay.
Exactly. So when it costs so much, and this experiment was never done, and there are maybe dozens of hyperparameters that you need to pre-decide on before you run the single expensive experiment, then you better have something between a rule of thumb to a complete theoretical understanding. Anything there would be good, not just hunches. Another motivation for the principal guidelines in this atmosphere is the fact that these models are so big and so expensive that the situation is it's very centralized right now. Only maybe 10 companies are able to train these and then serve and deploy them. And we got to ask whether we can, this was obtained by simple scaling, but whether we can achieve similar cutting edge, amazing capabilities by operating in informed matter with smaller models. So that's the motivation. My talk is work done in my PhD at the Hebrew University with Amnon's group. Mainly the theoretical work is going to be out of there. And done at AI21 Labs with this amazing group. Mainly the practical and empirical works are going to be out of AI21. I'm going to be talking about the transformer architecture, some works we published in NeurIPS and ICML. And actually, when the transformer came, in that moment, we in our group, we had a theoretical framework in place with which we analyzed the networks of 2017, 2018, recurrent neural networks and convolutional networks. And we were able to, in these years, show some connections between expressivity measures of convolutional recurrent networks and measures used by physicists in order to quantify correlations with quantum systems. I'm mentioning it here because it's actually a different talk, but if anyone's interested in these aspects, I'd love to talk about this. This is just to say that we were ready with a theoretical framework, and we're going to be, I'll talk about it and show the results. I'm going to talk about the pre-training process. Turns out that there are interesting biases introduced when you decide how to have your transformer traverse the internet. We'll talk about that. And what should be the objective? So when the transformer sees examples of raw text, what should you do with it? What should you teach the network to do? What should be the pre-training task? And I'm going to spend a good amount of time on what next. So this scaling approach has led us to amazing gains so far. But what happens beyond this paradigm of architecture and yeah.
Okay.
No, some issues.
People asking to minimize where's the minus
Sure.
or minus whatever.
A lot of animation on the top right coming up. Yeah, that's actually on the headline.
No, left out.
Thank you. Beautiful. Cool. So that was my intro. I'll jump into the transformer architectures if there are no questions so far. So cool. So this question of how to design the transformer architecture. Again, why is it interesting? There are reports that the next version of GPT is going to be 100 trillion parameters. Another 500x leap in size, another uncharted territory, and principal guidelines in these waters are important, as I said. And generally, when we talk about enlarging a neural network, there are two high-level things you can do. You can either add more layers and enlarge by that, or still more parameters per layer. And when I talk about depth versus width, this is when we're talking about deepening the network is simply adding more layers, and increasing the width is still more parameters per layer. And in particular, when I say the width of the network, I'm going to talk about the dimension of these representations that are being passed between layers. They're correlated to the number of parameters per layer. And the older sibling of transformers, convolutional networks, made their big splash in 2012, and it took them 7 years. But this paper called EfficientNet showed that if you're principled about how you increase depth and width in tandem, you can take the ImageNet top 1 leaderboard with a fraction of the parameters of the previous leaders. So this is important. I spent 10 minutes talking about how this entire NLP revolution is driven by scale. So our work is about providing these rules of thumb for how to scale up transformers with this motivation that was on comments. But an interesting preliminary that we need to ask before we talk about how to scale is depth even useful for self-attention? Which is a surprising question because depth efficiency and the premise of deep learning is about depth being more efficient than width and how concatenating more layers is more expressive. And indeed, in contests, when people solved optimization issues with residual connections, they were able to train hundreds of layers and that improved performance. So why do we ask that? Because OpenAI, a big player in our field, had this important paper about scaling self-attention, and they showed here in this yellow curve is a lot of networks deeper than 6 layers, and they showed the y-axis is the test loss, and lower is better. The x-axis is the size of the network, and they showed that the performance is mainly dictated by the size of the network, regardless of the depth to width ratio. They tried a lot of different depth to width ratios along the yellow curve, and it didn't really matter for their experiment. So that's why we need to ask: do you even need to deepen, or maybe it's enough to widen? That was a clear conclusion of their study. A small peek under the hood for self-attention. It's not an introductory, but for those of you who are familiar, it might help. A self-attention layer is a sequence-to-sequence function where the output at the output location I, the function there is a function of all the inputs in all input locations. So I'm going to schematically write this function. This is for those of you who are maybe somewhat know what self-attention is, but I'm not going to go into it. Schematically, what self-attention does is it sums over all the input locations over some pretty simple two-point function involving the input at the output location I and this running index j. Okay, so this is essentially a self-attention layer. And compounding self-attention again schematically, it would take me maybe 7 minutes to write it here on the whiteboard, but what happens if you reinsert the output of a self-attention layer again and again to the input of a next self-attention layer, which is a transformer essentially, then you get an exponential blow-up. The number of summons grows exponentially, an exponential amount of indices. Each summon now involves an interaction between the input at the output location and an exponential amount of inputs. So all of this is just to say that we're looking at self-attention, and it doesn't appear to be the growth with depth seems superficially exponential. So we have this on the one hand, this empirical signal that depth doesn't help. On the other hand, the whole entire premise of deep learning, we looked at self-attention, it seems to help. So what's at play here? So we reconciled it by using a measure of capacity for modeling input dependencies that we used in earlier works in our group. We used it for COMNETs and RNNs. It's called the separation rank of a function. It's defined for multivariate functions, and it's defined with respect to a partition of their inputs. So a partition would be a disjoint partition would be where half of the inputs are defined as subgroup A and the other half is defined as subgroup B. And what you need to understand about the separation rank, I'll show the definition, but the bottom line is that the higher the separation rank, the more this function correlates the two input subsets. And the formal definition of the separation rank is, maybe in words, it's the minimal number of separable summons that can sum up to give you y. Okay, so y is our multivariate function. You write it as a sum, and the separation rank is how efficiently, with how little amount of summons can I write the function where each of them is a function over the inputs in group A times a function over the inputs in group B. So for example, if you have separation rank 1, means that the function y is completely separable with respect to the partition AB. In a statistical setup, it would model no correlations between them, and this is the measure. And the higher it is, the more correlations modeled between the subsets. We connected this measure to quantum entanglement measures. I'm not going to go in. This is the different talk that I described. What we did here for transformers, we took the self-attention, the deep self-attention function. We bounded its separation rank, and we showed, maybe surprisingly, maybe not, that there's a depth efficiency regime in self-attention where this separation rank grows exponentially with depth and logarithmically with the network width. Yes.
How difficult is it to compute the separation rank?
It's a theoretical measure. So to compute for a function is difficult. To bound it, there are methods which we use. So this is a theoretical result, and this is essentially upper bounded and lower bounded by this dependency. So we wrote down the deep sum attention function, and we showed that the minimal number of summons to write it has this dependence. Yes, sir.
Can you relate it a bit to essentially graph superability type measures that were previously used for graphical models? But it seems to be conceptually similar, right? You decompose essentially your complex formula into subparts by conditioning on variables, right?
Sure. Yeah,
And,
earlier.
it was always work on tree width and stuff like that.
Yeah, so definitely one of our earlier works that I mentioned in quantum physics, this one, showed that you can relate this separation rank measure to a min cut if you put the inputs in subgroup A on one end and subgroup B on the other. You find the min cut in the graph between them, and it's really related. Okay, so yes.
It seems, well, maybe I missed it from the definition, but it seems that applying a linear transformation could take the rank, really increase the rank, even though it's not really changing the problem.
I'm not sure you can do it with a linear transformation. Do you have an example?
So if you have some x1 times x2, and now you apply the linear transformation to these, then now you have a lot of summons, right?
You have. So you have the number of summons grow like the dimension of your matrix. So and this exponential separation we need an exponentially sized matrix, which is not what happens in networks. So yeah, you can grow it, but not functionally dramatically unless you do something dramatic. So okay, good questions, and I'll go back to the story here, because in our story we said that transformers don't seem to be depth efficient. And we found a depth efficiency regime for transformers, and it turns out that this dependence only holds until the depth crosses a width-related threshold. Actually, a pretty practical one, because the width it grows logarithmically with the width. Okay, so we showed that for the converse regime, when the depth crosses this width-related threshold, there's a qualitatively different behavior of this ability to integrate the inputs as measured by the separation rank. And now depth and width contribute equally to the separation rank. Okay, so this is a theoretical result that came out of the framework.
So with respect to existing models, with
Respect to convex, for example,
yeah. So like
Mhm.
GPT.
you don't see the saturation, the depth efficiency in convex.
So it's only in the first regime.
Yes, this is what, for example, Nadav showed a few years ago. And so this analysis was the first one to give some formal grounds to this observed depth inefficiency, empirical one, but also predicted that the story is not so simple, and sometimes depth does help. And it was important for us to take this to experiments because there are a lot of moving parts in these systems. And we trained we had a pretty extensive empirical setup where we trained a lot of networks, hundreds, not more. What we showed is, for example, focus on the middle graph, is that if you have a 24-layer network versus a 12-layer network, and the x-axis is the size of the network. So in different size regimes, either 24 would be significantly better or 12 would be significantly better. So the two regimes manifested in practice, which was cool. And it allowed us to answer the preliminary question of, I have a budget from my bosses to train a 1 billion parameter network. What should be the depth to width allocation? Okay, so we were able to provide this very practical graph. Interestingly, the experiments conducted by OpenAI and the networks that they released, a lot of the networks that they're working with and they're offering to clients are suboptimal in the sense that they could be improved for the same size. They can be improved by deepening. Okay, so these networks are too shallow and can perform better if they were deep. And interestingly, in the other direction, their 175 billion parameters, the famous GPT-3, is actually too deep for its size. For the same size, which is 175 billion parameters, it could have been shallower, which means that they overpay, because if you're using a deep network, you're going to pay more for inference. It's less susceptible to parallelization. And at AI21 Labs, when we trained our follow-up a few months after them, we adhered to the guidelines, and our network is 20% shallower, and it had its merits. And also others in the industry, this BigScience collaboration, over 100 groups trained their model about a year after us with the same following the recommendations, and also Deepmind's Chinchilla model, which is great, followed it. So this was helpful, and it's also helpful in the sense that when we look to the future, to future networks, larger ones that people are talking about, 100 trillion kilometers, our fit is not very accurate when you take it very far, where the error bars just grow. But functionally, there's a clear recommendation here that if you want to reach this another 500x, maybe you should deepen by a factor of 2, but the rest should go to massive widening. This is clearly indicated by our fit. So this has a lot of implications on hardware and so on. It's going to be a big engineering feat anyway, but just to know that you're not missing out on the scale. If you're widening, I think is important. Yes.
Shouldn't training set size somehow play into this as well?
Of course, there is the size and the compute. There's a lot of papers on that. So this is controlling for the number of training examples. Beyond empirical follow-ups, our framework allowed us to answer other questions regarding transformers. So not only about how to scale, there are internal considerations inside the transformer, and we identified bottlenecks that leading architectures at the time had. Albert and T5 by Google were actually suboptimal, and they actually changed their internal configuration afterwards. Also, we showed how to apply transformers in other domains. We identified a bottleneck that has to do with the input dimension. So if you naively apply a transformer over images, over pixel RGB values, you're going to dramatically underutilize the strength of the transformer. And we showed it. So there are recipes for how to alleviate that by patching and by applying a convolutional network before you insert it to the transformer, which people use. Other groups have followed up and compared transformers to multi-layered perceptrons, which are people talk about in vision that we could replace transformers. But I'll spend some time now on our extension of this framework to apply to the pre-training domain. And this is going to be the next line of work.
Yeah.
So any questions? Yeah.
Still a question about the previous part.
Sure.
So far you have been discussing exclusivity, right?
Yes.
Is it really or is it really the bottleneck in scaling up performance? Because we know in other domains, but you couldn't this problem.
It's a great question, and I found language modeling to be a great setup to probe expressivity, because there's an infinite amount of data, for example. So you can see it that if we increase the network by 2 or whatever, so you see the loss decreasing. We haven't saturated the training set, and there are generalization and optimization errors, but we see a lot of correlation between results attained on expressivity and predictions to what happens in practice. So it's open, but I have a good feeling about it by now, and I think the language modeling is a good setup for that.
So the ability to train the model, it's not right. I mean, because in other domains, we know that if you take wider models, you might not even be able to train them at all, like reach a good training error.
So that's actually a good point for crazy widths. I think it should be addressed. If you go around these, like, which is practical stuff, it doesn't appear to come into play. But this is a good point about the scaling and like experiments that we haven't done before. So it's a good point. Okay, cool. So I'm talking about pre-training now, and at a high level, this is a process where you take the entire web, and you end up with a model. And breaking it up a little bit, there's this stage where you take just it's trillions of tokens in the web, and you decide which you batch them. You decide which get to go jointly into the transformer architecture. So the pre-training task is the transformer intakes maybe 1,000 tokens, not more, and it denoises. This is the task. I'm going to talk about it later. But the purple arrow here is a decision which 1,000 tokens get to go together into the transformer, and what people do is just naively take contiguous chunks of text from the internet. And this is a slide explaining why this is a slightly non-trivial situation to be in for pre-training. So in images, it's very straightforward. There's a training set, and each example is just a picture from the training set, and you perform a task on that picture. So we all know this paradigm. In text and pre-training, so there's the entire web, and there's a degree of freedom of what gets to be an example, what text gets to go together into the transformer. And this is a plausible thing that people do, this contiguous chunking. But what if I told you that there's a story about a dog and it's mentioned in different locations in the internet? So maybe this would be a better training example where I just take all the sentences around this dog and I put them together into the transformer. So there are no tools to discuss this. Does it even matter? It's unclear. And slightly more formally, are intra-example correlations better modeled than inter-example correlations? There's a hunch that yes, and we show theoretically that yes. And before telling you about our setup, I'll just mention that as a question, it's a modified expressivity question, because the classical thing I just discussed is about, and a lot of people, a lot of other works do. There's an architecture, and you ask how expressive the function implemented by this architecture is with respect to the inputs. Okay, so two sentences go together into the input, and how good is this function in integrating them? And the question that we ask is about the training process. So in this setup, the sentence S1 comes into the training at time step T. And then there's a loss, and the weights are updated via the gradient update mechanism. So the network here is red because it knows something about S1 via the gradient update mechanism. And in the next time step, the sentence S2 comes in, and the interaction occurs by this inputs to network interaction. And more importantly, the S1 is stored very loosely within the network. Okay, so we try to quantify that, and the question is, after all of this function that knows about both sentences, how expressive is it in integrating the two sentences? So what we showed is that for similarly, the in-context setup is what we had earlier, a depth L with the X network. This separation rank grows like the depth and the width similarly. But we had to work with a finite precision version of the separation rank, because if you think about it intuitively, in an ideal setting, when you have infinite precision in the weights, you can store maybe the data set in whatever decimal place. But in a real setup, you don't have more than 16 decimal places, this process is lossy by definition. And when we integrated this effective version of the separation rank with the sequential mechanism that sees them at different time steps, we were able to upper bound the ability to integrate the sentences in this mechanism with a toll that's taken here with the learning rate. Okay, so this learning rate is the term with which you update the gradients, and we were able to insert this optimization parameter into the analysis. And it makes sense, because if the learning rate is 0, then this network knows nothing about S1, so there's no integration. And the larger the learning rate, the more accessible S1 is, but you don't want it to be large for optimization issues. So for common values of the learning rate, we guaranteed a depth deficit. And call it depth deficit because it came out of the deepening, interestingly, the depth side of the analysis. So it's a weaker integration mechanism by at least 6 layers, and it's probably a loose upper bound, probably could be bounded more effectively. And this is a result that formalizes motivation for existing retrieval approaches that, even though the network saw this Wikipedia page during training, it still gains something by seeing it again right now in context. And this is sort of gives a formal grounds to say that. And also it indicates practical methods. We suggested this training setup where you think about how you prepare the pre-training examples, and you put nearest neighbors around concepts in context together rather than contiguous chunks. And we showed that you're able to you understand these concepts better if you do that. So this brings a degree of freedom of what text gets to go into the pre-training examples. I'll move to the pre-training task. Bird made a big splash, but it's a pretty simple task. So it's just about masking words and predicting them. And you see that the network learns something about the world via this task, because the Empire State Building in New York City, if Bird needs to predict the word located, then it understands now where the Empire State Building is located. But what if I told you that this word was randomly chosen for masking? I'd argue that it's a weaker training example. Any ideas why? Why this is not the best training example?
That you can tell new from new, you can tell it has dependency between new and York, so you can
exactly.
Tell, yeah.
So there's these local hints that if I told you New Mask City, you in your head would complete it. And Bird doesn't really need to know the entire story about the Empire State Building and so on in order to predict this word during training. So it turns out that it matters. What different training examples contribute differently. And if I were to mask New York City, then again, that would be good, because now Bird needs to predict the entire concept based on the context, which would help the network understand. And people have figured out that this masking matters. So in blue is the regular word prediction task I showed you. And the work by Facebook showed that if you mask contiguous spans here in red, then your probability to mask New York City increases. And which was the right intuition. In our work, we attack this principally and try to identify these correlated engrams and mask them. And it turned out to help the ability to answer questions about the world and so on. So because these correlated n-grams are abundant in language, and our masking strategy would essentially mask one of the important bits of the sentence, and it does so for any corpus. It's not about training. It's just you can put it in any corpus, and it improves training. So it's about looking at the language, the underlying data, and understanding correlations within it that helps you improve the performance. Another work, which I'm not going to go into, I'm going to mention, tackles another aspect of the fact that it's language. There's an underlying meaning dimension. So the word bass here is not a bass guitar, but it's a food, it's a fish. And when we injected the word sense information during pre-training at a wide scale, it allowed the network to know more about word meanings, which turned out to be important. So this is a time to recap because I want to talk about things beyond. How much time do I have left now?
19 minutes?
Oh, 19. Good. Okay, so recap. So far, we talked about the revolution that occurred years ago, 3 to 4 years ago. How transformers were important and scaling them was important, and we provided guidelines for how to do so. Also, the pre-training phase of how to traverse the internet is an important pillar. And we talked about how if you think about how we design the pre-training examples and about the task, you can improve and make progress. But the question is it enough? Should we just keep doing what we're doing? Scale the networks up, scale the data up, and these robot scientists will replace us in a few years. It's not trivial to say yes or no here, which is an interesting time to live in, because prominent figures in our community, a research director in Deepmind tweeted, "The game is over. It's all about scale now. It's about making these models bigger." And a Google engineer claims that their language model is sentient, self-aware, which is, and then Google fired him. So I don't know if it means that it's true maybe, or it's not true. And like more seriously, GLUE, the general language understanding evaluation benchmark, was broken by Burden and his friends. So people convened and proposed super GLUE, which was not supposed to be broken by these models. And within less than a year, this is human performance. We're number 7 on this benchmark. And here's the largest model in the world right now by Google. So it's hard to answer this question, but still I'm gonna talk a little bit about inherent weaknesses of the current paradigm, some of which we're working on, and also about the fact that this field is moving so fast, and networks that we have right now are unprecedented in size and in data, and there's untapped potential of what we have in our hands now before we jump to the next scale. And finally, just a few slides about how maybe to combine these and what the next generation of language models can look like, and why it's important to think about that. Okay, so I'll start with what's wrong with the scaling, what won't be easily improved. So if you ask GPT-3 or our network Jurassic this question, John and I split 12 apples between us, and he gave one to his son. How many apples did he have now? Okay, so they're going to fail on this. There's composition involved. You need to make calculations, and language models fail on this. But this is maybe explicitly multi-hop. If I just ask you guys, did Aristotle use a laptop? You know that he didn't, but it has to do with when he lived and who he is, and when was the laptop invented.
You said explicitly, you meant it implicitly.
Yeah, here it's implicit, but still it happens. Still there's a convoluted composite thing at play here. Turns out networks are very bad at these questions. Okay, so GPT-3 is far behind human performance. This is a work, by the way, by here at top by Mo.
He didn't want to waste his time on trivial things. That's why he didn't use it.
Exactly. But still, you see, this model PALM is 3 times bigger than GPT-3. So there is some improvement. So maybe we should just keep scaling. A smarter thing that people do today is that they show the model demonstrations of decomposing the task. Okay, so they say, John and I split 12 apples between us. How many apples does he have now? And then they show it the answer 6. And now John has 6 apples and he gave one to his son. How many apples does he have now? And then they show it how to reach the final answer with this intermediate supervision. And they do so sequentially. They just put the text into the same language model. The language model picks up on the fact that it needs to decompose. Called chain of thought prompting and Scratchpad. We have cool names. So what we did with this is that we proved a result for this sequence to sequence setup, where we showed that tasks that are unlearnable with any end-to-end gradient-based, in an end-to-end setting, tasks that are unlearnable with gradient-based mechanisms can become learnable, become polynomially learnable with SGD if you show them this decomposition. So this is a theoretical work that kind of supports the existing practice of addressing this drawback with using intermediate steps. Another drawback of these models is just factual information. There's a good example that stuck with me, so I'm paying it forward. Barack's wife Hillary, a few years ago, you ask the model Barack Obama is married to, and it's going to say Hillary. Why? Because it's a female name, and she's co-mentioned a lot with Barack Obama. And it's an example where word statistics beat the facts. Also, you say Barack Obama was born in, well, he was born in Hawaii, but he was senator in Chicago. So these models, it saw during training that he was born in Hawaii, but the word statistics, again, beat the facts that it's a location. And what people do is that they look, as I said earlier, they look for the Wikipedia page and they show the model at inference time, the facts in order to make it factually accurate. So this is the mitigation for this weakness. Work that I did with Oli over here, is about just showing these Wikipedia pages simply in context during inference. Really is all you need to do, and we replaced more convoluted mechanisms that people use in how to show the Wikipedia page. Another weakness here is if you just ask it a math question to add two numbers, it will do so okay if the numbers have 2 digits, but it's going to start failing if for 3-digit numbers, add 2 3-digit numbers, it's going to start failing, which if we think about our favorite AI figure from the 80s and 90s, quite embarrassing. He was a computer, very analytical, and it's an interesting time where AI helps us with creativity and writing texts, poems and so on, or generating art, but they're not good at adding 2 numbers. And sometimes, and this is what we did in AI21 earlier this year, you just need to know when to call a calculator, because this API of a calculator does this operation robustly at 100%. You still need a strong language model in order to infer what should be the inputs of the calculator. But this is a different interaction and not just an end-to-end attempt to answer math questions. So there are weaknesses and there are mitigations. This can be expanded beyond basic arithmetics to just generally APIs that perform operations robustly. So a bit about weaknesses. Now I'll talk about some of the potential that the models have. Our industry has this custom in the past few years to have huge papers with a lot of authors. This was our response. A lot of ideas and engineering experiments, great fun, standing on the shoulders of giant prose and language models with a pun. The premise here is the fact that it's very expensive to serve, even hold this model and serve it to clients. But this scale gives us magic. So our clients want the 178 billion scale power for paraphrasing and for summarizing and for Python and for thousands of use cases. And it's not feasible to just hold a model that does all of this at the scale. So what people do is that they externally prompt the model. They hold just one of these, which is hard enough. Not a lot of people can even do that. And they externally prompt it with natural language. You just say, please paraphrase, or please summarize, or please understand Python right now. And surprisingly, this works. And other methods have improved upon this and trained some small number of parameters here to replace the text, and this even improves more. And in our paper, we identified an opportunity because the scale is 178 billion parameters, and people use either no trained parameters or a very small amount of trained parameters. And we identified an opportunity to have a small network the size of the original BERT from 4 years ago that understood language pretty good. It was the state of the art 4 years ago. And by having a BERT model process the inputs before prompting the huge giant, and having a model that really understands language well, but on the other hand is negligible in size with respect to the giant, so no impact on inputs or anything, we were able to provide better prompting that's more attenuated to the input itself. And generally, the premise of standing on the shoulder of giant LMs is having these small BERT modules in the input and the output. And we also discussed this BERT module that takes the output and reinserts it back into the input. If you think about it, it's a way to get double the compute from a model that we have now. We spend millions of dollars with this model now, and you can get double the compute instead of pre-training a twice as large model. And you can make this decision per input. Maybe there are inputs where you don't want to run it twice, so you don't need the huge LM. So it's a way to decouple computation and memorization capacity, where the current just enlarging the model paradigm sort of marries and couples them together. And if you think about these, there's a lot more we can do now. So we show that by running the LM twice, we get to performance that no method that runs once through the LM can get to. So there's untapped potential of current scale. Okay, now let's just spend a few minutes on maybe how the next generation of language models can look like. So we talked about the fact that they have inherent weaknesses, composite input, factuality, and how the current paradigm of scaling is making progress and traditionally has. So that's why people are continuing to do that. But also the fact that per weakness, there's a solution module that's pretty effective. So this is what we talked about: composite inputs, factual accuracy, basic arithmetics. Also, if you need more compute, for instance, there's a solution module that we propose of running through the LM again. So maybe a picture to think about is a system with a smaller language model in the center that only makes decisions of when to use each solution module, instead of just answering each input black box with the same machinery. And these small BERT models around it would control and make decisions. So the canonical example proposed here, did Aristotle use a laptop? Maybe the BERT doesn't solve it immediately, but understands that we need intermediate steps. And then produces, when did Aristotle live? When was the laptop invented? And again, given this input, the model can just answer, but also maybe we should turn to Wikipedia to get the accurate answers for these questions, and get the Wikipedia page of Aristotle living in 300 BC and the laptop invented in the 80s. Again, now the language model, that's what they do today. They attempted answering this, okay? But maybe just an external API that compares two dates, the two happened before one, is more robust. It's like two number addition. It would sometimes work and sometimes not. So understanding when to turn to external APIs or when to use proposed solution modules can give us, first of all, the correct answer, but has the merit of maybe a hope for size reduction of the networks used, which is important for decentralization, as we discussed. Also, the output's going to be more reliable and more interpretable because we're going to know what the API call was. Obviously, there are challenges. Okay, there's the question of how to get supervision for this planning, maybe reinforcement learning methods, because we have different levers and we need to understand when to choose each. There's some hope. Turns out that language models pick up this planning ability during pre-training. A lot of magic is happening. This is one of the magics. They start decomposing composite tasks into steps. Another challenge is the interface between neural and discrete modules, different neural networks talking to each other. This is generally not solved and has a lot of issues. But there is a hope here that these language models, language is an ultimate interface for communication between humans, and these networks are very good at language. So maybe they can communicate by language. And what we showed that maybe if they learn how to communicate in a neural fashion, it could be more efficient and better. But these are open questions. And generally, whether it's this modular approach or another, it's time to think about a principled progress avenue with theory to chart the boundaries and maybe highlight opportunities, and a strong practical leg, because a lot of this is about engineering and finding the things that work. And that's it. I'll take questions now. Yes.
I have a very naive question regarding depth versus width.
Yes.
Does it make sense to try to interpret it based on locality versus globality that
Yeah, of course. Yeah, it does. When I mentioned the min-cut result from earlier, what we showed way back is for convolutional networks that shallower layers are more important for the local correlations, and deeper layers are more important for these global correlations. In convex, it's very straightforward because the inputs don't get to even see each other. Distant inputs don't get to even see each other until deeper layers. So that's why it was important for convex. And self-attention is a different mechanism where each layer sees all the inputs. And that had to do with the conjecture of what's different between self-attention and convex. But it's a good hunch.
Just two comments. One, I must give you a compliment. I think your emphasis on scale in AI is just absolutely fantastic.
Thank you.
about 40 years ago, a number of us tried to bring that emphasis into AI. For the record, I can tell you we failed, but there wasn't the industrial use. But there were people like Marv Minsky, Danny Hillis, our group, Woody Shapiro, and others trying to bring parallel computing into AI because of scale issues. The AI community at that time was not interested, but probably because there was no industrial use. And I think it's so incredible. It's just really amazing. We do have a question about the technical challenges. So right now, the attention mechanism is applied to data once it's in memory, right?
Mhm.
But if the data is spread on like disks across, is there a way to apply attention across partitions like that, or?
Yeah, of course, very relevant. One of the results that I showed now is about the fact that the transformer underutilizes information if it's not in context. So it's an intuition that we actually try to formalize. And there's a lot of energy around expanding the context window and having just attention be somehow more more extendable because it grows quadratically with the size of the sequence. So there are contesters that we talked about with Amir earlier. There are rivals to the throne of different architectures altogether, not attention. They still have a lot to prove, I think. And also, it's S4 for those of you who know about it from Stanford. And of course, Jonathan, sorry. Sorry. Yeah, but my thought about it is that any contester that does well on the long range, because of your good intuition, needs to also battle attention on the very practical window of 1,000, 2,000, 3,000 tokens. Attention is amazing there. And if you win both worlds, obviously you're amazing, but there's a lot of usability and short texts. So that's maybe what the battle could be about.
So your result about the conditional expressivity, where you have S1 and S2, next if I can go back to the slide. So
Only 200 slides.
I know, I'm sorry. So you use only two related contexts, right? And your it's called the Untapped, right? The method.
Mhm.
And based on like the let me start from scratch. Conditioned on that during training, it's you've trained on one example and then you wanna predict another example. So based on the fact that you've seen the other example and it's in context, you're able to model the expressivity increases, right? That's what's happening. Based on
I think if I understood you, then roughly yes, but I'm not sure I understood you.
so what causes the expressivity increase is what I'm asking.
Oh, okay.
Here.
Yeah, it's essentially about the gradient update mechanism here, storing information about S1 with the learning rate factor eta, which is small, okay? And our result is about how the smallness prevents these two sentences from really mixing as if they were shown without this attenuation factor, because here in the input, there's no attenuation. S1 is shown straightforwardly to the network. And it's important to attenuate, of course, because you try to cram in the entire Wikipedia into network weight, but we show that this takes a toll naturally. Yeah. And I thought you had a question.
Yeah, so at the end you were talking about how you can make maybe the language model smaller and then they can act as controllers that kind of like various operations. But if you think like separating out language and knowledge is really feasible, the right direction in some sense, a lot of the decision we as humans, if that matters, we don't have this separation, and a lot of our control, a lot of our planning is conditioned
Of course.
on knowledge of language, knowledge of the world. So don't you worry that basically you need this like in a single like package to be able to do planning properly.
Good question. I'll shoot it right back at you because us as humans, right? I don't know anything on Wikipedia. I can't perform any calculations that my calculator can. And like there is the small model at the heart, it shouldn't be too small. It should be something that we had a few years ago that any university lab could have. A few billions of parameters maybe, but do we want all the esoteric examples? Is that the right mechanism for that or for computation? Or so there's a question on that. And also it's like the system thinking fast and slow, system one, system two. So maybe you should you should use it, but then you should have an external mechanism that calls upon it several times. This might be also what's happening in our brain. So I'm not a brain expert at all, but I know that I don't know all of Wikipedia and I can't do the math. So, and that's an analogy with me. But of course, maybe scale would win out anyway. Yes. Oh.
Let's thank the speaker.